happy February, and thank you very much for attending today's talk. Can you hear me and see the slides okay?
We can hear you and we can see the slide. Oh, now it's better. There was a little kind of fuzziness in the slide, but that's gone.
Okay. All right. So today I am going to be talking about dispersants and dispersed oil. And as I started putting this talk together, it's part of this series. And you'll remember that in March I did 2 talks last March. One was on crude oil and what it was, and then the second talk was on what happens to crude oil when it gets in water. And this talk, series 2 of the Tuzzy talks, consists of 2 parts. The first is biodegradation of crude oil, which I talked about 2 weeks ago. And then this set of talks is on dispersants and dispersed oil. Can you hear me okay?
Just fine.
Okay. So I started making this presentation and I realized there's no way that I can give you a good talk on dispersants and dispersed oil and do it justice by just doing one talk. So what I've decided to do is to break this into 3 talks, okay? And I'll have to work with David Onley, as to when I can schedule these other 2. But I really want to give you an in-depth discussion of dispersants and dispersed oil because I know this is a critical issue for you, and it's one that you asked me to talk on. So that's why I'm going to go and break this into 3 different talks. So I hope that's okay with you because there's so much material to cover that I think it really does need 3 different sessions. So today, I'm going to talk about, or I'm going to review some of those properties of oil that are key. And then I'm going to talk about dispersed oil and natural dispersion only, okay? Natural dispersion only. So today, what the talk's going to consist of is natural dispersion. We're going to talk about relevant oil properties, what dispersion is, what affects how spilled oil disperses at the surface of the water, and also if you have a subsea release, how dispersed oil is transported, and finally what happens to the dispersed oil droplets. Okay? Everybody set on what I'm going to talk about today.
Yo.
Okay. Next time, I'm going to talk about chemically enhanced dispersion. That's where you add chemical dispersants, and then we're going to talk about how adding chemical dispersants to the oil affects the natural dispersion. And then what are chemical dispersants, and how are they used during response, and how are they applied, and then what happens to chemically dispersed oil and to the chemical dispersant. And then the last talk I'm going to do is on the effects of dispersants and dispersed oil, which is also a very complex topic. And we're going to talk about what's in dispersants, and whether dispersants or dispersed oil are toxic, and what we mean by toxicity, how toxicity is measured, and what we currently know. I just spent last week at a meeting down in Mobile, Alabama, where I ran a dispersants forum, and also where there was a whole day of this conference dedicated to dispersants and what is the ongoing research. So I'm going to talk about that in talk number 3, okay? But today, I'm going to talk about natural dispersion because we need to understand that dispersion of oil occurs naturally. You don't need chemicals to do it. The chemicals enhance the dispersion, but first we have to understand what dispersion is. and what it means to have dispersed oil, okay? All right. How's this going? Okay for the speed, etc.?
It's good.
Okay. So, relevant oil properties. Crude oil composition. This is something every time we refresh on because it is key to what happens. So you'll remember that when we look at crude oil, it has many, 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 many compounds. And they go from being these very, very small compounds, and this methane gas is going to come back. We're going to talk about that later today, way at the end of the lecture. And then it's up to these very, very large molecules. And the key is that the most dominant molecule or atoms are carbon and hydrogen that make these up. Okay, so we've got simple molecules to complex in the crude oil. Okay, now the next thing to remember is that crude oils have many, many characteristics, and I'm only going to focus on a few of them that really are relevant to what we're going to talk about today. We have to remember, though, that crude oils vary from place to place and over time from the same place. So we've talked about this many times. So it's hard to make generalizations about how a specific oil is going to behave because that oil can change over time coming out of the oil reservoir. Okay, so let's talk about some of these characteristics and just review them. You'll remember we talked about the density of the oil, okay? And the density of the oil is basically telling us how much mass there is per volume. And remember that we concluded that when we looked at oil, it was less dense than water. So here's water at, here's water at 1 gram per mil, and a milliliter is very, very small, less than a teaspoon. So that's water, and crude oil's less dense. So remember, it floats on water, okay? All right. Now the second property of oil that we're going to focus on, and it's going to come into play today, is viscosity, all right? And remember, viscosity of an oil is how resistant it is to moving. Does it flow easily, all right? So water, we know, flows really well. It's very mobile. Honey and molasses are less mobile. They have a higher viscosity. And remember we said that oil has different viscosities depending on the type of oil, but that the colder the temperature, the more viscous any oil is. The third characteristic that we've talked about several times now is solubility. And remember, solubility is how something wants to dissolve into water. And we concluded last time, and back in March of 2013, that something like sugar is very, very soluble in water. But crude oil, those individual compounds in crude oil are not very soluble in water, okay? And that, in fact, the colder the water, the less soluble they are, okay? So basically, if we review this, water is, most compounds that are in oil are not very soluble in water, okay? So those are some of the characteristics of oil that we've talked about several times and that we're going to see come up when we talk about dispersed oil. So what happens now when oil gets into water, okay? And you'll remember that we have several processes that occur. And today we're going to focus on this red one, dispersion, all right? Last time we focused on biodegradation. This time we're going to focus on dispersion. Okay, now this is the picture that we used during our discussions back last March about the fate of oil. And this is a very, very complex picture, and it talks about all the many things that can happen to oil once it gets in water. Primarily, that it floats on the surface of water, which you can see here's the slick up here floating on the surface of the oil, okay? But that there are lots of other things that can happen. The first thing I'm going to talk about today is spreading. And the reason I'm going to go back to spreading is because I want you to understand that spreading is different than dispersion, okay? So what is spreading of oil? All right, we talked about this last March, and remember that if you put a drop of oil on the surface of water, and you can go home and do this. If you have a pan of water, and you put a drop of oil on the surface, you'll see it starts to spread really fast, okay? And that it typically spreads in something similar to a circular pattern, all right? And that if we add wind, if you blow on that oil, it will start to elongate in the direction in which the wind is blowing, all right? But the key thing is that the oil goes from being thick on the surface to a very, very, very thin layer, okay? And we can predict, and we talked about this last March, just how thick that layer will be. But the spreading occurs until the oil reaches some very, very thin layer, okay? Now, how does oil spread? Well, oil spreads as a function of its viscosity. So if we have a light, free-flowing crude oil, it tends to spread very, very quickly. The thicker the oil gets, the more viscous it gets, the less it tends to spread. It will spread, but very, very slowly, okay? So typically, when you see something like a very heavy bitumen maybe, or an asphalt hit water, it spreads very slowly. It almost forms pancakes and spreads very, very slowly. Whereas when you have a very, very light crude oil, or even motor oil or engine oil from an outboard, you know it spreads really fast because that's light and free-flowing. Okay? So this is a graph that we used last March, and it basically shows that the thickness of the oil in inches over here, the thickness of the oil in inches over time. And notice that this is a medium crude oil in the first 48 hours or 2 days with calm seas and low wind. And this was a spill of 2.6 million gallons of oil. And you can see here that the thickness drops really fast, okay, to be less than 1/100 of an inch thick within 1 day. So the act of spreading happens really fast, especially if we have a light or a medium crude oil. And it doesn't require wind. You see, it doesn't require very much any wind. It'll just happen naturally. And it doesn't require any waves. It just happens naturally. And if you go home this afternoon and put that drop of oil into your dish pan, you'll see that it doesn't take anything, it just spreads. And this happens because of some of the interfacial tension between the water and the oil, okay? Dispersion is different. And now we're going to talk about dispersion. Dispersion is different. So let me stop right here and ask if you have any questions. Any questions?
Seems like we're good.
Okay, am I going around the right speed?
Yep.
Okay,
Thumbs up.
great. Okay, so here we go with dispersion, all right? So there are two types of dispersion. One of them is horizontal dispersion. In other words, it moves kind of in this direction, horizontally, all right? And with oil, with horizontal dispersion, it's the movement of the oil away from the point of spill, okay? And basically, you are getting movement by drifting and movement of oil in the water, okay? Now, this horizontal dispersion is largely a function of the wind, the waves, and the currents, okay? How the oil moves. And this horizontal dispersion, unlike spreading, takes days to occur, all right? Spreading occurs in about 1 day. Horizontal dispersion occurs over long periods of time. The other type of dispersion is vertical dispersion. That's in this direction, up and down, okay? So we can get dispersion of oil and water downward, okay? And this happens when small droplets of oil are created by turbulence, okay? So for example, and I'm going to show you this in more detail, wind and waves can cause the droplets to break away from the slick. They cause the slick to start breaking up into little droplets, all right? So as they get mixed into the water, they start to move down by the action of the turbulence. And I'm going to show you some videos of this. Some of those droplets, when they're in the water, can move up because they're too big to stay down, and they resurface. The larger droplets resurface. The tiny droplets stay down in the water, okay? So the first thing you see here is that the droplet size is key, okay? And I'm going to write that right on here because I want you to remember that, because it's really, really, really important that the droplet size is key, okay? So droplet size, oil droplet size is key. You're going to see that. I'm going to show you data that explains and shows you that that's critical. The smaller droplets, when they move down in the water, are going to stay down in the water. The bigger droplets are going to be less dense, and they're going to float back up to the surface and basically go back into the slick. Okay? So, the amount of dispersion is a function of the wind speed. Now, this is at the surface. The wind speed, the oil viscosity, or the thickness of the oil, the thickness of the slick, and several other factors. And we're going to talk about what those factors are. Okay. So what we just talked about was the oil forming these droplets, as you can see right here, and the resurfacing of the larger droplets. Okay? Small droplets, very small droplets, stay down in the water. Big droplets resurface. This is all about vertical movement. Okay, and to reiterate, what's important is the oil type and its characteristics, like its viscosity, its density, and environmental conditions, like temperature we're going to see is important, wind, waves, currents, and tides. Okay? All right. Any questions? Thumbs up, thumbs down. Any questions?
Good. We're good.
Okay. All right. Okay. So, the first thing I need to do is, I'll bet that some of you remember the concept of diffusion. Okay? And you've probably learned about this in school. And what it basically means is where atoms or molecules move from an area of high concentration to low concentration. where they're more prevalent to where they're less prevalent. This is a very slow process, okay? It's not dispersion, all right? So hopefully, is this going to work here? Yeah, let me get this.
It was on that thing.
Yeah. Oh.
Control was used.
Okay, hold on, let me get out of this and show. Hold on one sec. I'm having a little bit of a technical difficulty here, but hopefully this is going to work. Okay. All right. So I've got this wonderful little video that I want to show for just a couple of seconds that talks about dispersion, and I hope you can hear this. Oh, hold on. They can't hear it. So, they probably can't hear this. You probably can't hear this, can you?
No.
Okay.
No, we can't hear it.
I'll talk you through it. Okay? So basically, what this is showing is random motion of molecules. All right? The molecules are just moving around here. All right? And they're evenly distributed throughout the solution. That's throughout that beaker of water. Now let's think about what happens if we put a cube of sugar into this water. So you can see all the different molecules in the cube of sugar. And here goes, we're going to drop this cube of sugar into the water, okay? And now watch what happens. By molecular movement, just natural movement of the molecules of sugar, they have energy and they start to move out from where they're in high concentration next to each other to where they start to spread out to lower concentration and get evenly dispersed, evenly diffused, throughout the solution. Okay? Everybody clear on that? So what governs this process of diffusion is the molecules and their energy, and they're moving from an area of high concentration of themselves to an area of low concentration of themselves. Okay? That's molecular diffusion. Right? And molecular diffusion is very, very slow. Okay? The only thing that makes these molecules move is their natural energy and the movement from a high concentration of themselves to a low concentration of themselves. That's what governs molecular diffusion. If we had to wait for molecular diffusion to occur in an oil spill, we would be waiting a heck of a long time. Okay? What we deal with in oil spills is dispersion. And in dispersion, what happens is you break something up or separate it. Okay? And when you have dispersion, what you have is actually little particles or droplets that are suspended in a medium. Okay? So this is not a molecule dissolved. Diffusion is all about dissolved molecules. Remember how we talked about oil doesn't like to dissolve in water. So what oil will do is form little droplets in water that are suspended in the medium, in the water. Okay? So this is not solubility. It's droplets of oil dispersed into the water. Okay? And the amount of dispersion, the amount of those droplets that get into the water is a function primarily of the mixing energy that is in the environment. Okay? So it's different than molecular diffusion because the oil doesn't dissolve into water. The droplets are there. Very little dissolving of oil occurs into water. It's the droplets that are going to get broken off of the oil slick by mixing energy. Okay? So let's look at a dye in water. Now in this case, this is a dye, and dyes are oftentimes not soluble in water. In other words, they're little particles of color, little tiny drops of color that don't go into solution. So they're little tiny drops, and here's an example. Okay? All right. So you can see here comes this dye, which is sinking through the water, and see how it becomes diffuse, how the dye starts to spread out? What's happening there is that the little particles of dye are starting to disperse throughout the water. See that? See it dispersing throughout the water. As they fall down, in this case, the mixing energy, okay, in this case, the mixing energy, let's just watch this again. That mixing energy is coming from the droplets, this dye, falling down through the water. And you can see that the dye starts to spread out because the little droplets of color that are not dissolved in the water are starting to spread out. Okay? And you can see it becomes more and more dispersed over time. Okay? Now, let's take and look at another example. This is a very similar example. So here's dispersion of dye in water over time. Here's the start. The drop of dye goes into the water. It's got all these little particles of color dye in them. And as you drop it in, usually you squirt it in with a syringe or a little eyedropper type thing. And you can see it's got some energy because we've squirted it in. And it starts to fall down because it's got that energy. And as it falls, you can see it's the little droplets of dye start to mix in with the water. And here they are. And now it hits the bottom and it starts to move up. And you get all this dispersion over time. So the sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? That's dispersion of the dye in the water. And eventually it'll get to be a uniform color. Okay, so let's take a peek at what's going to happen here. All right? So let's just say this is my oil. Okay? So what's going to happen now is in that oil are all these, the oil is all one kind of giant slick. Okay? And what's going to happen is if I add some mixing energy, if I mix it up, if I add mixing energy. So in other words, let me do this by just, in this case, I'm just going to make a little paddle. And I'm going to make a little paddle, and I'm going to stir this up. And if I stir it with a lot of mixing energy, all right? If I stir it with a lot of mixing energy, then what's going to happen is I'm going to now create little droplets of oil. So I start to get little droplets. All right? I get little droplets of oil. All right? Blink, 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 depending on how much mixing energy I put in there. All right? So the key point here is that what happens with natural dispersion, with crude oil dispersion, no chemicals added now, just the natural dispersion, the oil slick gets broken up into droplets. All right? Here it's shown in something I already drew. So you've got the oil slick and you've got the droplets. So the oil slick is floating on the surface of the water. We add energy, typically by waves. That's the most common energy. and the oil breaks up into droplets. Now the key thing to note here is, look at this. The droplet sizes are different. And that's really important to note. The different droplet sizes. Okay? Not all the oil breaks into the same size droplets. All right. Everybody set on the concept so far of dispersion? If you are, just raise your hand. Okay, good. Any questions? Okay. So, what are the key factors that affect oil droplet size? Well, we've talked about mixing energy, and I'm going to go into that in a lot greater detail. The type of oil and its viscosity is important. The amount of oil weathering, the seawater temperature, and the salinity of the water. But the one I'm going to concentrate on first is the mixing energy, because this is really the key thing. These other factors will affect it, but the mixing energy is the key thing. Okay. Whoops. Okay. All right. Is everything okay there? I hear an alarm going off.
Yeah.
Okay.
For
No fire drill?
one of our members had a call.
Oh, okay. Okay. All right. So lots of times what you hear when people start talking about mixing energy, and they're scientists, they talk about turbulence. It's the same thing. All right? And the sources of turbulence in the water are many. There are some that I'm going to not cover, like ocean eddies, because usually they're not strong enough to engender a lot of dispersion. Langmuir circulation, which is another kind of surface phenomenon, again, usually not strong enough to cause a lot of oil dispersion. But there are other things, like boat wakes, that can cause dispersion because there's a lot of mixing energy from the propeller. Okay? The thing I'm going to concentrate on during our talks is basically, oops, let me get this into a different color, is waves, because that's at the surface of the water. That's the key form of mixing energy. And the waves can either be wind-generated waves or storm-generated waves or other kinds of waves. But basically, this is the most common form of mixing energy for oil spills at the surface, when you have the oil on the surface. Okay, so just a couple of facts about waves. So when you have a wave, right, you've got the crest of the wave, which is the top, all right? You've got the trough of the wave, and the wave height is the difference between the trough and the crest, and the wave length is the length from crest to crest, distance from crest to crest, okay? Now, I'm talking really about oil and water. I'm not going to really talk about oil along shorelines and dispersion along shorelines, but it's pretty much the same kind of thing. So when you have waves, okay, it turns out that if we look at the water movement or particles, as the wave goes in this direction, all right, here's the wave passing through the water, all right, you get the most movement up near the surface. So the water moves where a particle moves. Let's see if I can change this color here for a second. Whoops. The particles or water moves in the opposite direction, if you want to think about it, to how the wave is moving, all right? So up here at the crest, notice everything moves like this, and when we're at the trough, everything moves like this, okay? So depending on where you are, all right, let me do this a little bit differently. I don't think I made this clear enough. Let me erase this here. Oh, right. Oh. Okay. So if we look at how the water is moving, right up here at the top, you'll see that it's moving, whoops, it's moving like that, okay? And here it's moving in the opposite direction. Here it's moving in this direction, okay? So this is how movement is occurring under the wave. And you know what? You probably know this if you've ever been in a beach and bobbing up and down in the wave. The second thing to notice is that as we move down in the water column, the effect gets less and less. So the most effect of the wave is up here near the surface, and the least effect of the wave is down here below. Okay? So as we go down in the water, there's less effect. Most of the effect is up at the surface. But where does the oil slick occur? Up at the surface. So it's really what's happening at the surface that's very, very important to our natural dispersion. Okay, so what happens if we look at a wave moving in this direction is that here's a particle now, and when the first wave goes by, the particle starts here, and as that wave flows past it, whoops, as that wave flows past it, it ends up moving over to here. But what it does is it takes this orbital path. It doesn't just fly from here to here. Okay? Everybody set. That's important because that's what the oil droplets are going to do too. All right? Okay. So, if we look at waves now, all right, so waves, there are three types of waves that I'm going to discuss. Surging waves, which are also called regular waves, okay? And you'll notice that they don't break at all right? So that's just kind of your wave that gently moves through the water. There's no breaking. Then there are two types of breaking waves. So this is a non-breaking wave here. Doesn't break. And then there are two types of breaking waves. One is the plunging wave, and the other is the spilling wave. Okay? Now the plunging wave, if we look at the plunging wave, let's look at this a little bit more carefully, the plunging and the spilling. If we look at the plunging wave, you see how it makes this big front, and basically it plunges over. Okay? This is the kind of wave that really, comes along and thrashes over you and makes a lot of turbulence. So this is high turbulence, high mixing energy. You can see here with the spilling wave, it doesn't really have that big crest. It kind of spills over onto itself. All right, I'll show you some pictures. So this has medium energy for mixing. And the surging wave, of course, has very low energy for mixing. All right? Okay. So these next 10 slides I'm going to show you are by some work done by Ken Lee and Al Venosa at the Canadian Department of Fisheries and Oceans with some wave tank studies that they did. And in this case, they used two types of oil. One was a medium South American crude oil, and the other was your Alaskan North Slope crude. So the oil that's the medium crude from South America, is going to be labeled Mesa, and the North Slope crude from Alaska is ANS. All right? So here's a picture of their wave tank. Okay, so this is about 3 feet across. It's a long, thin tank. And you can see the 3 types of waves that they tested in this wave tank. One is the regular or non-breaking wave. See it right here? That's the non-breaking wave. And you can see it's kind of gently going through the water, no crashing. All right? The second type of wave is the spilling breaking wave. And you'll notice that in this case, the wave starts to crest, but this front of water just spills over, and it doesn't crash over. Whereas the plunging wave, look at that, you've got lots of energy. And again, going back to our picture, the regular wave, the plunging wave actually crashes over, and the spilling wave, the water kind of rolls down the front of itself. Okay? Everybody okay on the 3 types of waves?
Mm-hmm.
All right. So, now, here's something to think about. This is some data that they collected, and it's looking at the water below the surface. And the first type of wave they looked at was the regular wave. And here is the regular wave. I'm going to just highlight the regular wave here in yellow. There's the regular wave right there. And you can see that the regular wave does not have any real change in energy. It's just the same all the time. Just kind of rolls along with the same energy. Most of the energy is at the surface. It's the same energy, just the same energy all the way from the top of the water column, which is over here, to basically as far as it goes. So there's a couple things to notice here. All right, I'm going to go slow here. So the first thing to notice is that when we're looking at this picture, this here, all right, this is the water surface right here. All right? And this is 40 centimeters below the water surface. Okay? And a centimeter is about they're about 2.5 centimeters per inch. Okay? So it's not that far below the surface. All right? Okay. So you can see that not only does this regular wave have very little energy, it also doesn't go down. That energy doesn't go down very far in the water. In this case, it goes from the water's surface down maybe about 15 centimeters, not very far. If we look at the spilling wave, and I've got the pictures over here, so here's the regular wave in yellow, all right? Now I'm going to highlight the spilling wave in green, okay? So here's the spilling wave. And again, remember, it just kind of curls over and burbles down the front. So if we look at the spilling wave, this is it. It has obviously higher energy than our regular non-braking wave. So it has higher energy than the non-braking wave, and the energy goes down further in the water column. Okay? All right. It goes down quite a ways in the water column, about 30 centimeters. All right? The last wave, which is the plunging wave, I'm going to do in blue here, and here's the plunging wave. Look at how much more energy it has. Okay? So it has more energy, certainly than the spilling and regular wave, and that influence goes down quite deep. Okay? All right. So the type of wave we have is important because it dictates how much energy we have and how deep that energy goes in the water. Okay. Now this is another neat little set of pictures that Ken Lee and Al Venosa put together. Okay? And basically, here's the Mesa oil, and in a regular wave and a plunging wave. Okay? All right. So, here's the regular waves, and you can see at 5 minutes, and what these little colors mean is the more red the color is, the more concentrated the oil is. Okay? And so what's happening is, as we add an oil drop, and basically what they did was they added oil. They added oil to the water up here. And you see that and this is the length along the tank. So here's the beginning of the tank, and here's as the oil moves through the tank. Because remember, the wave is moving through this tank. So I want to show you what the wave is doing here. So the wave, and I'm just, whoops, that color isn't going to show up. So now this is remember, it's a regular wave, so it's kind of going like that. Real gentle through the water, okay? Just constantly these gentle waves flowing down through the water. That's this picture right here. You can see them. Here are the waves flowing gently down through the water. Oil was put on the surface of the water, and then they watched how that oil moved through the water. So here you can see, here's the oil starting out, and over time, the oil moves along the length of the tank. But look, it hardly moves along the length of the tank. And it doesn't move very deep into the water. All right? So it hardly moves along the length of the tank, and it doesn't move very deep. Here we have the plunging wave. Now remember, the plunging wave looks like this. This is the plunging wave. Lots of energy. And what you see with the plunging wave, again, the water's moving in this direction, but with a plunging wave, is, whoa, after 5 minutes, look at how far the oil's moved, and over time, basically, it moves down in the water column. All right? So what they ended up doing here is they put in more oil on a second run 60 minutes later, 60 minutes and 120 minutes. So this oil really, really moves through the water, okay, because of the plunging wave. Everybody clear that plunging waves move oil along the tank and deep into the tank, which means they move water rapidly out of the slick and down into the water column because they have so much mixing energy. Okay, now, remember what I said, that droplet size is the key, right? Droplet size is key, the oil droplet size. So what these guys did is they measured the size distribution of the droplets. All right? This is the regular wave. All right, so we're going to look at the regular wave. We're going to look at the spilling wave. And this is the plunging wave. Okay? So the oil droplet size goes from tiny, tiny 0, nothing, to, in this case, 1,000 microns in size. Okay? So, if we have a regular wave, look what happens, okay? You get a droplet size distribution that's very varied, okay? You get some droplets that might be really tiny over time, and you get some droplets that might be, or that are around this 100 micron range. In a spilling wave, you get a much tighter distribution, okay? Now, the key thing here to notice, all right, is that as we move to the plunging wave, we get a really, really tight distribution of the droplets, okay? All right, everybody set on that. Okay, the key thing to note is that the droplet size tends to be around 100 microns or so. Now, if you do a micron, say this here, a micron is about, so 1 micron is really, really tiny. You remember last week I was talking about bacteria being really, really tiny. 1 micron is really tiny. You would not be able to see 1 micron, okay? You need hundreds of microns to be able to see something. So this droplet size distribution you could barely see. Okay. So what kind of effectiveness, percent of dispersion, do we get, what dispersion do we get with a regular wave versus a plunging wave? Okay? So here's the regular wave, here's the plunging wave. We get maybe about, 8% dispersion with this Mesa, this South American oil, and with the Alaska North Slope crude, maybe a little bit more. With the plunging wave, we get more dispersion, maybe close to 20% with the Mesa, but it really doesn't make as much difference with the Alaska North Slope crude. That's because the Alaska North Slope crude is a little bit heavier than this Mesa oil, okay? So it doesn't disperse as well with energy, okay? So here you can see that the oil type does make a difference. The lighter the oil, the less viscous it is, the easier it is to disperse with waves, okay? All right. So here we are, again, just showing you over time, in minutes, how the oil is moving, okay? And this is time in minutes, how the oil is moving through the water, and this is with non-breaking waves with Mesa oil. Okay. Here's the spilling breaking waves, and here is the plunging breaking wave. So again, you see the same pattern we talked about. The less energy, the less movement. As we add more energy, we get more movement, both along the surface, or excuse me, along distance away from the source and with depth into the water. Okay, so this is the Alaska North Slope crude, and this is an example of what happens. Now, here's the key again with this droplet size. It's kind of strange, but when you put Alaska North Slope crude into a tank, over time, with regular waves, you get, and this is the size of the droplets over here in microns, the size of the droplets in microns. You get a lot of different sizes over time. Okay? Some really, really small ones and some really, really large ones up around 400. But the most of them are in this range here from about 300 to 200. Okay? If we have a breaking wave, you can see, and I'm going to highlight this in yellow, if you have a breaking wave, you can see that over time you tend to have a much tighter distribution. More of the droplets are in this size range of about 180 maybe or so microns. Okay? So if you want to get lots of smallish droplets of an even size distribution, the breaking wave is better. Now, of course, we don't control what types of waves there are. The types of waves are a function of the wind and whether you have a storm, right? Any questions about mixing energy, before I go on, about mixing energy and dispersion?
Is the micron measurement cubed to measure volume, or how is that?
Is it what?
Is it like a centimeter cubed? Is it a measure of volume, or is it sort of like a length?
Oh, no,
measure?
no.
The micron.
What they're measuring here is this distance. This is the droplet. Okay?
Okay.
Linear.
All right? Any question on that?
No. Thank
So
you.
it's basically the mean diameter of the droplet. All right? Any questions? So you can just about see these droplets at 200 microns. Tiny, tiny, tiny. All right? You okay with it now? The more mixing
Thank you.
energy, you go to plunging waves, you're going to get the oil mixing in better and deeper and smaller droplets. All of kind of a more uniform size. Okay? Any other questions? So the key thing to remember is when you went, or if you were at the spill down in the Gulf, and you didn't add
That's happened last time too.
Should I get the tech people?
I don't know if you
This is
can
Chris
hear
with
us.
video
but
conferencing. I can see. I'm on it.
Okay.
All right. Chris with NSA.
calling the service number.
Yeah, he said he was on it.
And Peter's going next to see if we can get the bring it back.
Okay.
Is it frozen or?
Hi, hold on, it's not done. It's not done. Somehow we got disconnected. All of a sudden it said, call disconnected, so we're not exactly sure why, but hopefully you'll see my slides again here soon.
Do I have to do that again?
Yes. Okay, here we go. So, other things that affect droplet size are the type of oil, and I showed you that with the Mesa versus the Alaskan North Slope crude. The more viscous the oil is, the harder it is to disperse. So the South American crude was a little lighter, it's a medium crude, versus the Alaskan North Slope crude, a little more viscous, harder to disperse. Okay, another thing that affects the amount of dispersion is how long the oil's been in the water. And you'll remember that as oil stays in the water, we talked about the fact that some of the lighter things, some of the lighter ends, the lighter compounds, are going to, they're going to actually disperse into the water, or excuse me, not disperse, they're going to evaporate. So some of these lighter ends are going to evaporate. Some of these things are going to break down by photolysis, etc. So as the oil weathers naturally in the water, you get more and more of these heavier compounds, and they do not disperse well. So as time goes on with the spill, there's less and less dispersion of the slick, because the oil is getting to be compounds that don't like to disperse into water because they're more viscous by nature. The oil becomes more viscous. Another factor that you might be interested in is that as temperature goes down, dispersion becomes harder. Natural dispersion becomes harder. Again, the oil's going to become more viscous, right? As temperature goes down, the oil's going to become more viscous, so it's going to be harder to disperse it. Okay? Now, here's a little bit of an odd thing, that as salinity increases, dispersion gets easier. Okay? So if you have fresh water, dispersion is harder than it is in salt water, in seawater. And that's because the ions in seawater actually make it easier for the oil to disperse. It's an effect at the surface of the oil droplet that actually makes the oil easier to disperse. So if you were in an area where there was a lot of fresh water input into the ocean, you'd get less dispersion than if you were out in full-strength seawater. Okay? All right. Everybody set on what happens for natural dispersion in surface slicks. Okay? Now, in a blowout, like the Deepwater Horizon, it's different. So if you have a surface slick only, if oil is coming out of a ship, like it came out of the Exxon Valdez, and it's floating on the surface, then wave energy is what's going to cause the turbulence and the mixing and get the oil dispersed naturally in the water. Okay? If you have a blowout, like we did in the Deepwater Horizon, where you've got a source of the oil down deep, okay? So the source of the oil is down deep. Then what you're going to see is a different phenomenon. It's much more complicated. And we don't understand it as well. Some of the oil is just going to float to the surface, okay? Now, the shallower it is, the greater the chance that as that oil floats to the surface, it's just going to be a slick, as shown here, okay? And some of the oil, if it's a shallow release, may stay in the water from some turbulence that's happening down here by the release point. And some of it may sink, okay? But if you have a really deep release, as in the case of the Deepwater Horizon, you are going to have some weird things happen. Okay, so here we go in a deep water oil spill, okay? What you've got is the well down here, all right? You've got the well down here, and you've got two different phenomena occurring. One is what's called near field, which means close. It's close to the source. As you move away, you haven't moved far away from the source. And the other is far field, and that's as you move further away from the source. Okay? All right. What's going to happen here? Notice the current is going in this direction. And this is deep water, hundreds to thousands of feet deep. In the case of the Deepwater Horizon spill, 5,000 feet deep. Now, obviously, right off where you are in Barrow, the water is not that deep. But there are places where the water gets quite deep, way offshore and off the shelf. Okay, so we've got some different phenomena occurring here. First, you have your normal turbulence, okay? So let's take a look at this. Oops. Gotta just go back into this for a second. Okay, so this is from a, oops, that's not right. Oh, somehow I jumped back here. That happened, sorry about this. Okay, so this is a video from the BP or Deepwater Horizon blowout. And you can get these videos or see these videos. They have 550 of them, I think, from at the Purdue University oil spill website. You can go to that site, and there are just lots and lots of these videos. Okay? I'm just going to show you one, okay, of these videos. Okay, so here is, these are cameras, and you can see the oil pouring out of the well, all right? This is you can see it coming out here, and I think you can probably see two different colors, all right? And here it goes. See how it's getting bigger and bigger? Look at all that turbulence. That's because that oil is flowing out.
Well, there we are.
Hang on, I'm on it again.
Okay, sorry about that. I don't know why this is happening, but we'll just keep going. So I'm going to start this video again. So what we're seeing here is the oil is billowing out of the well, and you can see how it's just in a huge amount of turbulence because it's shooting out of that well, and you can see the plume is getting bigger and bigger, and there's a huge amount of turbulence. The reason it's changing color is the oil is getting mixed in with the water, and the turbulence of the oil shooting out of the well and mixing with the water is creating droplets. Okay? It's creating droplets. And you can see here, this goes on and on and on and on and on. So I'm not going to show you all of it. All right? But you can, if you want to watch it, you can watch hours of them. Okay, so you've got a huge amount of turbulence because the oil is jetting out of the well, and that is creating natural dispersion. All right? Now, the other thing is water's getting mixed in with that plume because of all this turbulence. Okay? There's something that's really also going on here that's very important, and you'll see this word hydrates right here. Okay, see that hydrate? All right, a gas hydrate, and you get these in oil reservoirs, is basically a little ice-like crystal, which is a mixture of water and natural gas. And what happens is, as the gas, some of what's coming out of that well is gas, because the reservoir has oil and gas in it. And as the gas comes out, it hits this cold water, and it forms an ice-like crystal with a coating on it kind of thing, which is a mixture of oil and it's a mixture of water and natural gas. So it's a mixture of methane and water, and it's cold, so it forms this kind of ice-like thing. And as it rises, that little hydrate decomposes and it forms just the gas bubble of the natural gas, the methane. And those bubbles also rise, okay? So this is a little bit more complex because we have this gas that forms these little hydrates that actually are like little crystals that go up, and then eventually the crystal decomposes and you get just the gas bubbles. So what you get, basically, though, from our position of turbulence, is you get this very, very turbulent flow. Okay, now I'm going to show you a little model of what actually happens because all the oil doesn't flow to the surface. This is a website of Carthy, which is one of the consortia looking at how oil flows. And here's their, well, maybe we can't show you this. Okay, here we go. Here's their little mathematical model of what happens. So here's the oil coming up, and you'll notice it's rising to the surface. It's getting more and more diffuse. And look at what's happening here. See these secondary little layers that are forming? Basically, what we think happened, or we know happened, during the deep water horizon is that you got this kind of plume that was rising up, and little subplumes came off of it, of dispersed oil. Okay? Go back to this. So what we had is, back to that, what we had is these little subplumes. Oops. This back on here. What we had is the main plume coming up, getting bigger, and then keeps rising, gets more and more diffuse. Some click up here, some droplets. oil droplets because of all of that dispersion, and some of the droplets peel off. You get dispersion of some of the oil droplets that are very small, and that's what you saw in that picture. So you get these, there it is, and you get these subplumes coming off like little trees almost, and some of the oil goes up to the surface and some of it peels off in these little plumes. And that's the dispersed oil, the naturally occurring dispersion that occurs in deep sea. Now, not everything disperses like that. Some of it does come up to the surface, but some of it we now know forms these little plumes that came off at different depths. Little plumes of dispersed oil droplets that we could track for kilometers. Okay?
Well, what's that? You have kind of a line. You have kind of a line in the middle. You can see the rig up at the top, and you can see the blowout at the bottom. But there's that line in the middle. Is
Neutral buoyancy level.
Yep.
Yeah, that's where you have neutral buoyancy. So that's basically where you have neutral buoyancy of the plume. Okay. It's where normally, if it was a sewage plume or something, it might start to move down gradient. You see how it starts to move here down away in the lateral direction with the current? You start getting horizontal movement. That's when you reach this natural buoyancy level. Okay? It's still rising, but as it comes, let me just try and show this a little bit differently here. Okay, so what's happening in this area where you have the near field, see that's the near field area, the plume is just rising. There's very little movement to the side. Once you hit the area of neutral buoyancy, you get a lot more movement to the side, and that's where you kind of get this area of far field. See, once you hit this area of neutral buoyancy, you now get far field movement. And it's still moving up to the surface, it's just moving laterally a lot more. You with me now?
And how do you define that line? What is it again?
It's where the density of the plume of oil is equal to, is close to the density of the water.
Okay.
Okay? All right. Okay, so we're almost done now. Really, once the oil is dispersed, it just travels along with the water. So wherever the droplets are, if they're in the deep sea, they're moved by deep sea currents. If they're in the surface water, in the surface water, you know, in the top, 10 feet or 100 feet, it's moved by wind-generated water currents. It could be moved by tidal currents. Whatever's moving that water, these little
Not too bad. I'm almost done, I guess.
I'm on it again. Not entirely certain why that's happening, but hopefully we can at least keep brute forcing this through.
Okay. All right, so are you there? I can't really see you, so, okay. All right, sorry about what's happening, but we just have to live with it, I guess. All right. Now, if the oil droplets are too big, they're going to resurface. They're going to move up, and they're going to coalesce and just go back and make a slick. But if they're small, they're going to stay down in the water, and they're going to move along with the water. So what happens to these tiny little droplets? Now we're going to talk about the tiny droplets that stay down in the water. what happens to the tiny droplets that stay down in the water? Well, some of those molecules dissolve out of the droplet. So here's the droplet, and it contains all of these different molecules, and those molecules dissolve into the water. But we know not much of this occurs because way back at the beginning of the talk, we remembered that very little of the oil is soluble in water. Okay. Another thing that can happen is, and what can happen to that oil if the oil dissolves into the water, remember, if it dissolves, we talked about last week, it can biodegrade. We also have observed that this is an oil droplet right here, and you can see on the surface of it these little microbes. So we know that microbes, little bacteria, can adhere to the droplets and biodegrade the oil in the droplets, though it's not as fast as biodegrading when it's dissolved in the water. Another thing that can happen, and this has been shown by Ali Khalifa up at Environment Canada, is here's oil droplets, and these little black things are sediment particles in the water. So if you were in a place like Cook Inlet, you might have a lot of sediment in the water. And you can see that the oil droplets, the tiny droplets, will stick to the sediment. Okay? They'll actually stick to the sediment. And so now you can see the little black dots with the oil all in this kind of mass of sediment plus oil. And they can sink to the bottom. We now know in the Deepwater Horizon that quite a bit of this occurred because of all the sediment coming out of the Mississippi River. There may be other things that happen to these droplets, this dispersed oil. We don't know. There's a lot of research going on about that. So, in conclusion, the things to remember about natural dispersion that I want you to take away from today's talk are that mixing energy is needed to get dispersion, natural dispersion. And the more energy, the smaller the droplets. At the surface, the mixing energy is waves, so if you have big crashing waves, you're going to get more dispersion and smaller droplets. And in a subsea blowout, the energy of mixing comes from the turbulence of that exiting oil. Okay? And the droplet size determines where the droplets go. The bigger droplets are going to go up to the surface and coalesce into a slick. The smaller droplets are going to stay submerged and move along and get biodegraded or mixed with sediment and sink, or maybe some other things happen to them. So next time, when we schedule this, we'll have to work with David on it. What happens when we chemically disperse oil? And then the time after that, what are the effects of dispersants and dispersed oil? Thanks so much. I'd like to open it up to questions.
What do we, of course this will be horrible if any of this comes up, but I guess I'm hearing that if it's in small droplets, it's going to get biodegraded, and that's a good thing, whereas the slicks are they a good thing in a way? I mean, or they're easier to clean up. So I mean, how does that play out?
Okay, so let's take that in little chunks. So let's say we don't have ice up where you are. Yeah. All right? Okay. If we have an oil slick that forms, all right, the oil slick can be easier to clean up, right? So if you have, we talked about this a while ago, we could skim the oil off the surface, right, with a skimmer, collect it with a boom. This was last year we talked about this. Collect it with a boom, remove it from the surface, that kind of thing. Unfortunately, that only works when it's fairly calm, okay? So if you have a storm or lots of waves, wind-generated waves or storm-generated waves, you're going to get natural dispersion. all right? So you're not going to prevent natural dispersion unless you have no bad weather or no wind. Okay, now, the bad thing about slicks of oil is that they tend to be problematic for birds, and they tend to be problematic for marine mammals. So whales, etc., sea otters, that kind of thing. They tend to be problematic because those organisms, those marine mammals, come up through the slick to breathe, and if they get into a slick, they can get coated or ingest the oil or whatever. And birds, if they land in it, they may get it on their feathers, hypothermia, issues of ingestion as they preen to get the oil off, all those kinds of things. So there are issues with oil slicks that you don't have with dispersed oil, but it's all a trade-off. The key thing about natural dispersion is you're not going to stop it, okay? It's going to happen. As long as if you have waves, breaking waves, you're going to have natural dispersion. So that's the thing I want to have you take away from this. You cannot stop natural dispersion in a spill. Okay?
Yeah.
Any other questions? Next time we're going to talk about what we do and why we decide to add chemical dispersants to enhance this dispersion. But right now, the thing you need to remember is natural dispersion will always occur in a spill because rarely do we have calm weather conditions throughout the length of a spill. Now, the other thing is... Excuse me?
I was just going to ask, are there any studies ongoing, or have there been studies about the effect of ice on this dispersion process?
Yep. Okay. So, good question. The minute you put ice in the situation, right? You know how you folks know much better than I do that the ice has leads in it, right?
Yeah.
Oops.
One more time.
But you said we're done.
No, one more time.
Oh.
Try and reconnect.
No,
Because
one
we
more
got
time.
5
We're
minutes.
almost done, but I'm going to try and bring her back.
Okay, I'm pulling up a talk, one of the talks I gave last year, and you wanted to know about oil and ice and dispersion. So this was from last year, and you'll remember that we said what happens is when oil comes up under ice, it can get trapped under the ice, but if there are leads in the ice, the oil will accumulate in those leads, right? But if you think about it, you probably know better than I do by a long shot that the turbulence in those leads, the waves in those leads are not nearly as big unless you have a very, very big wide lead or a long lead that you get a lot of fetch from the wind on. So what ice tends to do is if oil collects in the leads, you get less turbulence and therefore less natural dispersion. Okay? Does that make sense?
Yes.
Now, some of the work that was done or has been done by the Norwegians is that they actually put boats, if they have icebreakers that are going through the leads, they will actually use the propellers to create natural dispersion to get oil down in the water column. But again, that is not natural dispersion. That's where you use mixing energy from a propeller to do that. Did that answer your question?
Yes.
Other questions? I've put you all to sleep, I think.
No, it's great. Terrific talk.
Yes,
Thank you.
Okay,
thank you.
okay. So are you, I hope you're interested in hearing the other two talks.
Yes.
Yes.
Okay, so I'll work with David. Is David there?
No.
Okay. I'll work with David to schedule the next two talks, the one on chemically enhanced dispersion and the one on effects, because they're big topics that I want to talk all about what dispersants are and what's in them and all of what we know about that and how chemical dispersants are applied and do they help or don't they help to enhance natural dispersion. And then in the next lecture, I want to talk about what are the effects of dispersants. What do we know? How do we decide what toxicity is, et cetera, and what really is the toxicity from the dispersant chemicals or the dispersed oil or a combination. Okay?
Great.
Thank you.
Thank you.
Thank you.
Thank you so much for listening, and I've been hanging in there with all of it. Okay? How's the weather up there?
Warm.
Warm?
It's what?
24.
Comparatively, yeah, it's above zero. It's
26.
26 above.
Wow, that's something. Well,
Here in Fairbanks, it actually even go as far as to say it's freakishly warm.
Oh my goodness! Wow. Well, I will tell you that I was in Mobile, Alabama this week for this meeting, and they got hit by an ice storm. They had a ½ inch of ice on the roads and everything, and they shut the entire state down. So we were in these two hotels. No restaurants were open, nothing. We were all eating in these couple of restaurants. So it was quite something. They need to learn from you folks how to deal with snow and ice, and cold. So I'll see you in a couple of weeks. Thanks.
All right.
Thanks
Thank you.
again.
Bye.
Bye-bye.
Thanks, Chris.
You're welcome.
Yeah, I'm and
Thank you, Chris.
people die.
You're welcome. We're going to be trying to work
Thanks,
with
Chris.
University of New Hampshire to make sure that kind of stuff doesn't happen again.
Thank you, Chris.
Great.
I finally read the...
Chris, could you see a lot of the slides were kind of fuzzy and then they cleared up at various times? I don't know if you could
Unfortunately,
see that.
that's more or less just a bandwidth issue.
Yeah.
What?
Right. Gotcha.
Because we can only run these conferences at 386 kilobits per second, or 384. That's just kind of one of the things that is there.
Yeah. Okay. That was fine. They cleared up. I think we saw each slide well at some point.
Should
Well,
I
this is
leave
great
the slides
technology.
on? Should I leave the slides on longer then?
What you might actually
No,
consider
I think
doing,
it's about right.
what you might actually consider doing is sending the slides out with an email in advance so that they can kind of show them alongside as well.
Okay.
Or maybe even refer to them later if they
Okay.
needed to.
Okay. We can do that. Thank you very
And
much.
the other thing
now.
I'm going to
Bye-bye.
suggest.
Oh, go ahead.
Bye-bye. Well, I was going to say, if here at Barrow, if we can move I'm going to talk to them about moving the screen closer to us because some of these great slides have smaller print, like I'm looking at the ice one here, and but it's a little hard to see unless you're pretty close. So that's just local. Bye-bye.
Okay.